Hi, everybody. This is Mr. Oops, I'm not writing. This is Mr. Folly, and welcome to 2.3. We're going to talk about trends and explain the trends. So let's go ahead and hop into them, all right? All right, sounds good to me. Periodic table explained. So size and nuclear attraction explains all trends. By all trends, I mean every trend. We're going to talk about size. We're going to talk about nuclear attraction, okay? Bond energy equals Q1, Q2 over radius squared. So if I have like Mg plus 2 and Cl minus 1, Q equals plus 2, and the other Q equals minus 1, right? And then radius squared this is just the size. Okay? So when I look at the periodic table, I see something that I think is pretty weird. Okay? So hydrogen's on the left-hand side of the periodic table and helium's on the right. I'm adding more protons, right? Psh. Wouldn't you think when I add stuff it gets bigger? It doesn't. It gets smaller. So that's why, so as you go to the right, it gets smaller to the right. So, oops, let me erase that. The important part is it gets smaller as you go to the right, okay? Now notice here, when I'm looking at my periodic table again, I'll look at my periodic table down here. I've got argon, I've got neon, I've got helium. Notice as I go up, it gets smaller. Why does it get smaller? It gets smaller because there are fewer energy levels, right? So see how this one has 1, 2, 3. This one has 1, 2. And this one has 1. And notice how it gets smaller, okay? So it's true for each one. So on the second row, if I'm looking at lithium and I compare it to neon, as I go through, it keeps getting smaller and smaller and smaller and smaller and smaller. Why does it keep getting smaller? As I go to the right, there's more protons, so it's more attractive and pulls you in more, right? So if you're more attracted to somebody, you want to sit closer to them in class. How you doing, right? So that's what happens. So more attractive people often have people sitting closer to them than me. There you go. All right, so the next trend we're going to talk about is electron affinity. And in electron affinity, that is the ability, and it's right down here, by the way. Oops, I did the wrong one. I did electron affinity, and I meant to do electronegativity. My bad. Electronegativity. They're almost the same. Ability to attract bonded electrons. So notice electrons I abbreviate as E negative. So if they're negative, that means they're going to be attracted to positive things, right? So as you go across lithium to beryllium, right, you have more attractive protons. Instead of 3, I have 4. Instead of 3, I have 5, 6, 7, 8, 9, 10. So see how this would be the most. Excuse me. You have more attractive protons, and you're a little bit smaller. Remember how I talked about it gets smaller? So more attractive protons, smaller, so you attract bonded electrons better. Notice how we talk about size, attraction, and then we define the trend. Okay, now this increases, again, the big increase, let me make this a marker, it increases a ton going this way. So what that means is the most electronegative element is fluorine. We do ignore noble gases. Now, what's the most electronegative in a column? That's also fluorine. Why? Now we're going up. If you go up, you get fewer energy levels. What? Let's take a look at that again. As you go up, you get fewer energy levels. Do you see how I have 3, then 2, then 1? And that makes it a lot smaller, okay? So you get much smaller. So if you're much smaller, you're also more attractive. Just being closer to someone makes you more attractive to them. Believe it or not, that works. So you attract bonded electrons better, okay? The equation for electronegativity. Remember how electronegativity is attracting an electron? Here's an atom, here's an electron, here's an atom that's attracted an electron. All right. And then that is ability to attract a bonded electron. Smaller size is more attractive. Fewer energy levels is more attractive. More protons, more attractive. Positive protons attract negative electrons. Next trend. Ionization energy, the graph's below. Okay, energy to remove a valence, that's outermost shell. Remember, that's S and P. Not just S and P, but outer S and P from a gaseous atom. Smaller size makes it more attractive, so it takes more energy to remove. It's harder to break up a couple and steal their girlfriend or boyfriend if they're very attracted to each other or if they're very close to each other. More protons is more attractive, so it takes more energy to remove. It's harder to break up and steal someone's boyfriend or girlfriend if the person they're dating is like super attractively hot. That makes it tougher. So you want to go after somebody who's dating an ugly, and then you get a better chance. Or just not try and cheat. Okay? So again, as I go across this graph, you should have these arrows. So these arrows. So who's the best one? Fluorine's the best one. Why? That doesn't make any sense to me. Why would that be true? Well, as you go across, you have more attractive protons. So look, 19, 20, 21, 22, 23, 24, 25, 26, 27. See how this? As you go this way, you get more protons. More protons means more attraction. So if it's more attractive, it'll also be a bit smaller. More attractive protons, a bit smaller, takes more energy to remove a valence electron. What did we say again? We talked about attraction, we talked about size, and we defined the trend. Watch how we do that again on this one. As you go up, okay, so as you go up, this part right here, as you go up, you get fewer energy levels, so you're much smaller. If you're much smaller, that means you're more attractive. So it takes more energy to remove a valence electron. See how we did it again? We had boom, attraction, boom, size, boom, define the trend. Boom. That's it. We're out of here again. So that I will say, toodles. Give me my theme music.